So welcome everyone to the first seminar, monthly seminars of, in this case, in the month of April. First of all, we wanted to remind you that from the 9th to the 12th of July in Madrid, we will be organizing the PYSQT 2024. Quantum Technologies workshop for young researchers. For more information, don't hesitate to scan the QR code that you are seeing in the shared screen, and it will lead you to the Benasque Science Center website with all the information. So we will be waiting for you all there. It's true that it's July and it's Madrid. It will be hot, but I'm for sure we will have a lot of fun. I think Alonso was there the last year, and I think he enjoyed the experience. So
yes, it was very nice.
So I encourage all of you to join. And okay, having said that, I think we can start. We have here Alonso Hernández. We studied physics together in Zaragoza. Then he has gone to Switzerland, to the ETH in Zurich, under the umbrella of the professor Andreas Walraff. And he will give us a seminar today about generation of 2D cluster states of microwave photons using superconducting qubits. So I'm sure it will be a pleasure to have Alonso here giving the seminar, and please start when you want.
Thank you, Jesus. Shall I share my screen?
Sharing? Yes.
All right. Can you see it?
Yes, we can see it perfectly. Don't worry.
Good. Okay. So thank you very much for the introduction and for letting me give this talk today here. I'm really pleased to be here today. I'm going to talk about the generation of 2D cluster states of microwave photons using superconducting qubits. And well, I am going to start basically with a small outline. Probably many of you know already that superconducting quantum devices have been demonstrated to be applicable in many fields. In many technological fields, they are a platform which can be used to make quantum computing processors, error correction experiments, single photon detectors, quantum optics and wave acuity experiments, quantum communication. It has a very broad scope of application, and this is what I want to talk about today. So I will first start with an introduction about the basics of what these devices are like and how to operate them. And then I will focus on an application of them, which is the field of quantum optics in the microwave regime of frequencies, and how to use these devices to generate photonic graph states and cluster states. So let me actually use a pointer. Yes, here. Okay. Well, as a very good story in physics, we're going to start with a harmonic oscillator, how to make that with superconducting circuits. If we have a so-called transmission line resonator, that's just a cable with two capacitors in the ends, and we send an electromagnetic field through it, this field is going to form standing waves within this cable, and we're going to have standing waves in electric and magnetic field inside it. So these standing waves are going to have a fundamental mode and some higher excited modes, and are going to have a certain frequency which depends on the length of your cable, of your transmission line. If you measure the transmission through that, you send a signal through port 1 and measure the output in port 2, you are essentially going to measure something like this, a transmission peak, like the one you see here, around the frequency corresponding to the length of this resonator. So the way to realize this, actually on chip, if you want to make useful and scalable devices with it, is with a coherent waveguide, which if you make a picture of that, it's going to look something like this. And the structure that it has on the chip itself is that you have a substrate of silicon, which may have some layer of oxide on top of it because it just appears naturally on this material. And then you're going to pattern a conductor on top of it, for instance, niobium, which is a metal. And then essentially you can pattern the center conductor here with a certain width, which is going to be what is going to actually conduct the signal that you're going to send through it. And you can also pattern a ground plane on the sides from it, which is going to be your voltage reference in this circuit. Alternatively, one can also make this with an LC circuit. So if you just connect the two plates of a capacitor, it's just going to discharge exponentially, and it's going to relax to having 0 voltage difference between the two paths, assuming there was some difference at the beginning. But if you now put an inductor in parallel with it, this inductor is going to give inertia to the electronic current, meaning that your signal is not going to relax exponentially anymore, but it's going to oscillate. It's going to behave as a harmonic oscillator with a frequency depending on the capacitance and the inductance of this circuit. Essentially, if you measure what's happening in the circuit, everything here is going to oscillate. The charge difference in the capacitor plates, the voltage difference, the current in the circuit, the magnetic flux through the inductor, they are all going to oscillate with the same frequency, omega. The way to realize this can be also done on chip on a two-dimensional architecture as well. And we would again have a silicon substrate, which is not conducting. We're not going to have any current through it. And then we will pattern this niobium on top of it. And with this niobium pattern, we can first use edges and distances between edges to engineer capacitances. And we can use also meanders or this kind of wiggles to engineer an inductance. The typical dimensions of these devices are some hundreds of microns, meaning that the resonance frequencies are typically around 4 to 8 gigahertz. Now, there's nothing quantum here yet. So if we want to make this behave as a quantum harmonic oscillator, we need to lower the temperature. If we lower the temperature, and the metal we chose is a superconductor, we didn't choose niobium just because. We could have chosen copper, but we chose niobium for a reason. At a low enough temperature, this niobium is going to suffer a superconducting phase transition, in which the electrons, which typically scatter with the lattice in the material in the niobium, are now going to see an effective attractive interaction due to this electron-photon interaction. And below the critical temperature, this attractive effective interaction is going to make them group into Cooper pairs, which are not anymore fermions, and therefore these statistics and scattering phenomena do not happen on them anymore. They are bosons, and they will be able to move through your lattice without resistivity, meaning that this material will become zero resistance, and therefore we will have a pure LC circuit. In the case before, the niobium at room temperature, for instance, would have some resistance, meaning that our harmonic oscillator would actually be slightly damped. When we go below this critical temperature, this resistive term, which gives us the damping, disappears completely. In addition to that, if the temperature is low enough, essentially we're going to remove all the thermal excitation in the system, meaning that we can access the lowest energy levels of this system. And we can deal with this in a conventional quantum formalism by using two variables of the circuit, the charge between the capacitor plates and the flux going through the inductor, which are conjugate variables, and they must, in this case, commute. Sorry, not commute, but have this commutation rule typical of conjugate variables in quantum mechanics. And one can deduce a Hamiltonian for this, which is happens to be quadratic with the charge in the capacitor and the flux in the inductor. It also depends on the capacitance and the inductance, of course. And when you have a Hamiltonian, which is quadratic on both conjugate variables, this behaves as a harmonic oscillator, meaning that you can define some field operators, and you know you're going to have a quadratic potential with certain energy levels, which are going to be equally spaced by a difference of energy h bar omega. If this harmonic oscillator was in the ground state and you now drive it, the final state is not going to be the one state, but it's rather going to be a coherent state in which you have a Poissonian distribution of populations of the excited states, essentially because all the transitions have the same frequency, meaning that with the same drive, you are exciting not only the transition 0 to 1, but also all the transitions in the higher levels, 1 to 2, 2 to 3, etc. So with this architecture, you cannot really confine your populations to the 0 ground, to the 0-1 manifold of your system, and you cannot really define a qubit like this. You don't have this addressability, and you cannot use this subspace as a qubit. Alternatively, the way to design a qubit like this is by replacing this inductor by a so-called Josephson junction. which is essentially a tunnel barrier for Cooper pairs. It's going to be a very narrow insulator barrier in the middle of the superconductor, which classically should essentially kill all your current. Of course, it's an insulator, there should not be current through it. But when you deal with quantum physics, actually, the Cooper pairs can have some tunnel effect, and they can tunnel through this barrier. If this is narrow enough, the damping of the wave function across the barrier is not going to be too bad, and you will have some tunneling rate and some Cooper pairs hopping from one side to the other of the barrier. The way to realize this, or at least the way we do it, is by using aluminum, which is a metal and is also superconducting. And so we can deposit a first layer of aluminum, then let it oxidize to aluminum oxide, just by controlling the concentration of oxygen and the duration of this process and the temperature, and then deposit a second layer of aluminum. And by sandwiching this oxide with the two aluminum layers, we're going to have exactly what we need: superconductor, insulator, superconductor. You can take a look of a micrograph of what this looks like. Here you can see two tips, vertical and horizontal, which are both aluminum. And in the middle of the two, it's not visible here, there is a barrier of oxide, which is the insulator that the Cooper pairs are going to tunnel through. So this is actually going to behave as a nonlinear inductor, in the sense that if we now use a different variable, not the flux going through this inductor, because there's no inductor anymore, but the phase difference delta between the wave function of the Cooper pairs at both ends of the junction, one can again write the equations of this system, and one finds that the term which was before quadratic with the flux, in this case becomes a cosine, meaning that we are moving from a parabolic potential to a cosine potential. It's not a harmonic oscillator, but an anharmonic oscillator. Or analogously, we can think that we don't have anymore a quantum spring, we have a quantum pendulum here. In this case, given this nonlinearity, we can, first of all, we can rename for convention the energy levels of this system as G for ground state, E for excited state, and then F, H, and so forth for the higher energy levels. And we can see that the transition energy in this case is not the same for all transitions, but it actually becomes different for each transition. Now, the transition from the first to the second level is different from the transition from the 0 to the 1 by this unharmonicity term alpha, which is, let's say, between 5 and 10% of the frequency of the qubit, or the frequency of this transition, or the magnitude of this step. So now we do have addressability, because we can use this frequency instead of this one to only drive the transitions between G and E and not excite any upper levels. And we can use this lower subspace indeed as a qubit. So now in this regime in which we can only use these two energy levels, we can essentially simplify all of our dynamics and deal with this in a much more user-friendly way, just by defining a qubit on it and dealing with a Hamiltonian just with a Pauli Z matrix, which is much more convenient. And we can use this qubit, and we want to do operations on it. So to do single qubit rotations on it, if we just want to do some operations on this qubit, we can use a so-called charge line, in which we couple a control line capacitively to our qubit. And essentially, if we send an oscillating signal here, we are going to be effectively sending this oscillating drive to the levels of the Hamiltonian. So we can operate this GE manifold coherently, and we can drive Rabi oscillations, define a Bloch sphere, and all these nice abstractions that we want to make when we want to do quantum information processing. Another convenient thing to have here, if possible, is to be able to tune the frequency of the qubit. Because, well, for many reasons, it's really useful to be able to say, okay, now I don't want my qubit to be at 5 gigahertz, I want it to be at 7 gigahertz, for instance. To do that, we replace the junction by a so-called SQUID, which stands for Superconducting Qubit, Superconducting Quantum Interference Device, which is essentially two paths with one junction on each, which is gonna, as the name says, produce some interference. And then when we have a magnetic flux going into this surface area, this flux is gonna induce a certain current around this loop, which is gonna allow us to control the resonance frequency of the qubit. So this magnetic flux will allow us to tune this resonance frequency. And for that, we are going to add an extra line to the system to control that. This line is going to be grounded right next to the squid so that the current here is maximal and we can maximize and have larger amplitudes of magnetic fields going into this squid. The effect of this is modifying the depth of the potential well and therefore modifying the transition frequency of our qubits. And this is going to be very convenient, as I said, to have a more flexible tuning knob for the control of the system. And when we want to have many qubits on a device, this is going to avoid issues like frequency crowding or other stuff. So let's take a quick break and see what this actually looks like. I want you to ignore in this picture the lines which are colored in blue and red for now, and see what we have around. So first, what you see here in dark gray is not really a conductor. It's just you're seeing the silicon substrate underneath your circuit. It's not really conducting current. But then what you see here in light gray and all the colored lines, which are, of course, artificial colors, are indeed niobium. So in light gray, you can see the ground plane, the so-called ground plane, which is our voltage reference, is what we draw as the lower part of the circuit here. And in yellow, you can see the central island, which is the upper part of the circuit that we have been drawing before. This central island, due to these edges which it has some capacitance to ground, which is the capacitor we have mentioned before. And also, we have a connection mediated by a squid there, which is the loop that I mentioned before to have this flux tunability. We also have many lines poking into the qubit. I said, let's ignore the ones in blue and red for now. But the one in pink is the charge line, the one used to drive the single qubit operations, coupled capacitively, again, by this distance to the central island of the qubit. And the one in green is the flux line, which we're going to use, as I mentioned, to control the flux going through the squid. The next building block we need to do actual useful stuff with these devices is to have 2 qubit gates. 2 qubit gates are also a necessary building block for a universal quantum computer, and they allow us in general to generate entanglement between qubits. The way, or the most standard way to implement this is by producing conditional bit flips or conditional phase flips on our qubits. So one of the most I don't know, academic, let's say, gates that one can think about is the CNOT gate, in which you have a gate involving 2 qubits. One of them is the control, one of them is the target. The gate, the control qubit is the one that is going to, let's say, decide on what's happening on the other. So if the control qubit is in the ground state, 0, nothing is going to happen to the state of your system. But if it's in the excited state, it is going to make a flip on the other qubit, meaning that the 1, 0 state is going to be mapped to 1, 1 and vice versa. Analogously, or equivalently, one can also think about a phase flip. There's this control Z gate, which is also quite relevant for the context of superconducting circuits, which does not do a conditional phase flip to one of the qubits, but it introduces a conditional phase, or introduces a phase conditionally on the state of one of the qubits. So the way to picture this one is if qubit 1, if control qubit is in the excited state, then we add a minus sign, a pi phase shift, to the target qubit. These two are actually equivalent. They can be mapped from one to the other by just single qubit gates, and just being able to do one of them is enough for universal computation, but different hardware schemes allow for different types of gates. In our case, this is not necessarily the most extended way to do these 2 qubit gates, but we use the so-called tunable couplers. So we want to do a gate between 2 qubits, and we are going to deal with the energy levels of these qubits, as I mentioned before, calling them or labeling them as GEF and GEF. So we can have the ground state, the common ground state of the 2 states. We can have qubit 1 being excited or qubit 2 being excited. We can have both being excited at the same time, or we can, for instance, have qubit 1 being at the second excited state and qubit 2 in the ground state. We have many more levels, but I'm not drawing them here. So to do these gates, we are going to introduce 2 paths to connect these 2 qubits. One is going to be fixed. It's just going to be a CPW, a coplanar waveguide resonator, as I mentioned before. And the other one is going to be a tunable path. It's essentially the same, but it has a squid in the middle in series with it. This squid is going to allow us to control the interactions between the qubits using a magnetic flux here. So this magnetic flux is going to be this parameter we are going to use to tune our interactions. So if we, for instance, have a superposition state on qubit 1, a superposition between G and E, and we want to swap that superposition to qubit 2, so that we want to move the populations from the state EG to the state GE, this is commonly known as a swap gate, we can send a modulation to our tunable coupler with a frequency which matches the difference between these two energy levels, delta. If we do that, essentially, we are going to induce a Rabi oscillation between these two levels in what is called a parametric gate. And it's going to make the population move from one level, to the other one, effectively enacting this swap gate. But this swap gate actually is not really introducing any entanglement. It's interchanging things between two qubits. It's moving things from one to the other, but it's not really introducing any correlations between them or entangling them at all. So we can think of how to do that and how to implement a control C gate, as which is the one I mentioned before. If we start with our system in a superposition of states which has some contribution on the EE state, we can do the same as before, and we can now mediate these Rabi oscillations between the EE state and the FG state. So when we do the first half of the rotation, this population is going to acquire a phase I, so a phase factor of I, which corresponds to a phase of pi half. And when we go back, when we do the second half of the rotation, we are going to end up acquiring a geometric phase in total of -1, meaning that we have left states GG, EG, and GE untouched, and we have introduced this phase on the EE state. This is exactly what the C set gate, the control phase gate I mentioned before, is about. So this way you can use this architecture to implement this conditional phase between your qubits. Again, let's go back to facts and what this actually looks like. You can now see a device with two qubits in them. As I mentioned before, they both have their charge line and their flux line for single qubit gates and frequency tunability. But now in blue, now I want you to look at these lines, is a tunable coupler. So there is one normal path connecting the two of them, which is this bare resonator. And there is one additional path, which has something here, which is a squid. This squid is again controlled by another flux line, as we did with the qubits. So this flux line would be somewhere here and allows us to mediate the interactions. And well, there is more stuff going on in these devices. There is, for example, readout circuitry, which is essentially, I'm not gonna go into details about it. I'm not gonna explain how it works. But it essentially allows us to distinguish the state of our qubits and to measure whether they are in the ground state or in the excited state. And this is, of course, going to be a very useful, well, not a very useful, a key component in most experiments in this field. But I'm not going to explain how it works in the interest of time. So yeah, let's put together all these building blocks that I've been running through before. We are saying that we're going to use the lowest energy levels of a nonlinear oscillator as a qubit. This is what we call a superconducting qubit. This is going to have a tunable transition frequency, which we're going to engineer with a squid. We can enact single qubit gates with a charge drive, so-called charge drive. And we can use couplers for two qubit gates. And in addition, there is some extra readout circuitry, which I will not explain. But the bottom line here is that this is a scalable architecture, which can be used for large devices with many applications. And now this opens many doors to us. So let me make a parenthesis first here and mention that there are some things which I've not really discussed and I will not discuss, but of course you are welcome to ask any questions you have. I have not discussed other schemes for two qubit gates like fixed frequency couplers, which are also very extended. Also not discussed readout. I haven't discussed the fabrication process, which is something really complex and where many people really have been putting a lot of work. Cryogenics, not either, because this is a completely different story and it would take a lot of time, and also electronics. These are all key parts of the process, which I'm not really going to focus on today. So I said we can use this, this architecture to make bigger devices for interesting applications. So here you can see a micrograph of a device, which was used for a quantum error correction experiment. And now you are probably able to tell the components in it after this first explanation. It has 17 qubits. It has charge lines for single qubit gates, flux lines for frequency tuning. It has couplers for the 2 qubit gates, and it has readout circuitry. And as you can see, well, there are many technical things to solve for these experiments, but essentially this architecture can be scaled up to many large devices. Now, let's think about what applications this may have. Of course, first of all, one can think of using this for quantum computing or quantum error correction experiments, which are at the forefront of the, let's call it, quantum race towards fault tolerance that many people are working on. They can also be used for the so-called noisy intermediate scale algorithms, which are the ones meant to be implemented and hopefully useful before fault-tolerant devices are extended. But this technology can also be used, for instance, to make hybrid devices combining superconductors with other materials, so with other architectures. For instance, semiconductor spin qubits, nanowires. It can also be coupled to spins in crystals. It can be coupled to mechanical resonators. It can be coupled to magnons, to many other physical platforms. So this is already a very interesting platform anyway. But the ones that we're going to focus on in the rest of the talk are the fields of quantum optics and many-body quantum physics. So, okay. The thing which I want to explain now is how to essentially open the doors to the field of quantum optics or waveguide QED with this platform. And I'm going to explain how to emit a photon into a waveguide traveling through it from a device like this. So let's assume we have a chip, whatever it looks like, which is coupled to a waveguide. And so in the components here, we're going to have a so-called storage qubit. It's just a normal qubit, as I've explained it before. Nothing special in it. It's going to be reasonably long-lived. It's going to have, hopefully, a good coherence time, and so on. And then we're going to have an emitter qubit, which is going to be very strongly coupled to a waveguide. This strong coupling means that any excitation that comes into the emitter, whenever we excite it from the ground to the excited state, this qubit is going to very, very quickly decay into the waveguide as a photon traveling through it. And then to mediate interactions between these two, we're going to use, as I mentioned before, tunable couplers. Let me, however, simplify this picture by just showing something like this, which is going to be more convenient. And now I will explain how to emit a photon. So we can think, or we can label the energy levels of the storage qubits as G, E, and F, for instance, for the first 3 energy levels, and the energy levels of the emitter qubit as 0 and 1. We are not even going to deal with higher energy states like the state 2, because as the decay from 1 to 0 is so fast, because it generates a photon due to this strong coupling, we are not really ever going to populate these higher energy states. So let's start by exciting the storage qubit with a pi pulse from the ground state to the excited state. We will now have a Fock state stored here in this qubit. And what we want now is to swap this excitation from this storage qubit to the emitter. To do that, we can drive this parametric transition or this parametric operation using the tunable coupler to send this population from the E0 state, which is the state the excitation is stored in the storage qubit, to the G1 state, where we store the excitation in the emitter qubit. And right after that, if we just wait, we are going to have the emitter decay very quickly into the waveguide and emit a photon into it. And this photon will be traveling through the waveguide. The chip will be back in its ground state, and we will have a Fock state, or whatever initial state we had here is going to now be traveling through the waveguide as a photon. What we call this photon is a photonic mode of this waveguide, which is not a standing mode because we assume this waveguide is very long. But it is essentially encoded in the population of this mode. So our zero of this photonic qubit is going to be having no photon in the waveguide, and our one is going to be having the photon itself. So if we have a superposition state between G and E and we swap it out, we're going to have a superposition between having no photon in the waveguide and one photon in the waveguide. We want to measure these photons. Of course, we want to see them. So what we do right after we emit them is that we first amplify them with an amplification chain using Josephson amplifiers and other low temperature amplifiers and low noise amplifiers and so on. We also filter the signals to remove some noise. And eventually we're going to have this photon with an RF frequency. Essentially, the photons are going to inherit the frequency of the emitter qubit. So if the emitter qubit is at 5 gigahertz, the photon will be oscillating at 5 gigahertz. And then as this frequency is too large and we cannot really sample it right away, we are going to down convert it using a so-called heterodyne detection scheme, in which we use a local oscillator, also at a gigahertz frequency, to down convert this signal to two quadratures, the real and the imaginary components of this unconverted signal, which are now at megahertz frequencies, lower frequency, and we can now digitize it and measure it with an analog to digital converter. We do that, we average over many, many shots. And for instance, if we take 4 million averages in this experiment, we can see a shape like this, in which we have a cosine growth first in this photon, which stands for the coherent exchange of populations from the storage qubit to the emitter, because this exchange is essentially a 2-qubit gate, which we have mediated coherently. And then the second half is an exponential decay, which stands for the release of the photon into the waveguide. But we do not only want to see them like this, we also want to do tomography on these photonic qubits. So to do tomography on them, we can record histograms of these IQ components of the field. We are going to histogram this electromagnetic field distribution. And this histogram we're going to find after many shots is going to be tightly related to the Husym-EQ function of the generated state. The Husym-EQ function is, for those who don't know about it, is some sort of Wigner function of this state, if that one sounds more familiar. From this histogram, we're going to compute the statistical moments of this probability distribution, essentially, of the electromagnetic field, which we do on a GPU because it's a very intensive task. And then we're going to feed those to a maximum likelihood estimation algorithm to infer the density matrix of the state of the photons, rho, which we're going to do using convex optimization on a PC. So after these two steps, first inferring the moments and then running the MLE processing, we are going to finally infer a density matrix of the state that we have generated. And this is, for example, experimental data of the density matrix we infer if we emit a photonic Fock state. So now I'll make another parenthesis to talk about an interesting field which we want to explore, which is the one of graph states, or in particular, photonic graph states. Graph states are a way to picture many-body entangled quantum states, in which we picture our qubits, or our photonic qubits, in this case, our photons, as the nodes of a graph. And then the entanglement structure of this big state is going to be encoded in the links or edges of this graph. This is not a very, let's say, a very orthodox way to say it, because there are some equivalence rules in these graphs, and it's not so straightforward. But the way you can picture it, if you want, is that when you have a set of qubits, those are the nodes of your graph. And then if you make 2-qubit gates between those nodes, you're going to more or less be assembling or building these connectivity links one by one. So this is a very broad field, which has applications, which has many applications. One of them is measurement-based quantum computation. So essentially, if you generate a graph which has the shape of a lattice, of a 1-dimensional, 2-dimensional, or 3-dimensional lattice, which is called a cluster state, you can use that one for so-called measurement-based quantum computing schemes. in which you do not have this standard picture of quantum gates and measurements and so on in your state. But what you do first is you prepare a huge entangled state involving all your qubits, and then which is always the same state, like it is always this cluster state. You don't need to change that no matter what algorithm you want to run. And then on a second step, you're going to translate all your gates and all your operations in your original algorithm. You can translate those to some sort of recipe of how to run measurements on this big entangled state. And essentially, this is completely equivalent, and one can demonstrate that one can do universal quantum computation with this approach. And it has also some benefits, like, for example, the fact that if you have a photonic state which is emitted on one side of a network, and then you can do the measurements which contain all the information of your algorithm on the other part of your network, this can be some sort of distributed fashion of computing in which you have a server and a client. The server always does the same thing. It generates the cluster state, and the client can actually do the measurements, which are the easy part of the algorithm, without caring about the most complicated part of it, with the server not knowing the algorithm that is running. So this would be a so-called blind computing scheme. More applications that these graph states can have are error-corrected quantum communication and one-way quantum repeaters, which have been proposed for short or long-distance communication between nodes in a quantum network, or metrology, for instance. Here, we are going to focus on the generation of two-dimensional cluster states, which are the ones applicable to measurement-based quantum computing, and therefore the ones that we are interested in, because they are these 2D cluster states. They are the reasons for this technology. So we are missing one building block to do that. We want to generate entanglement in these photons. To do that, we're going to use the same architecture as before. But now we are going to start exciting the storage qubit, not to the excited state, but to a superposition state. If we do that, and now we also are going to use some higher energy levels of our system, we can now do a pi pulse on the EF transition of our storage qubit, and then a parametric operation between the F0 and E1 levels of the system. And effectively, we're going to map the state E0 to the state E1, enacting a CNOT gate between the two qubits. And we were going to have now a Bell state between these two qubits. If we now let the emitter decay, we're still going to have a Bell state, this time between the photon and the storage qubit, meaning that the photon is going to be entangled with this storage qubit. We can keep doing this, iterating the same process, and we can essentially keep generating more excitations entangled with the other ones in a 1D architecture. This is how one would generate a 1D cluster state. So let me summarize the requirements for this then. We have these two qubits, this tunable coupler, which we use for photon emission and to generate the entanglement. And this was actually, okay, this can be used to generate 1D cluster states. And this was realized in our lab some years ago with an architecture which is essentially just like that. It's very straightforward, one qubit, the other qubit, and a tunable coupler. But what we want now is to scale up to two-dimensional cluster states. So we can add a second pair of storage emitter qubits, which would allow us to generate two 1D cluster states. But if we introduce one more tunable coupler here, we can now generate 2D cluster states with this device in the shape of a 2x(n) lattice, or what we call a ladder shape. The device to do that looks, again, pretty straightforward from this architecture. We have the two storage qubits, both coupled with a tunable coupler to the emitter qubits, also coupled to each other with another tunable coupler. And then both emitter qubits are going to be coupled to this orange line, which is the waveguide which we emit the photons into, which is going to be multiplexed in our case. Essentially, this means that the photons coming from both emitters are going to be sent through the same line and are going to be multiplexed there. And as the photons inherit the frequency of the emitters, if this emitter is at 5 gigahertz and this one is at 6, the photons emitted are going to be at 5 and 6 gigahertz. we can distinguish these photons in frequency afterwards, even though they are in the same line. So we can actually do just that and check this multiplexing. And if we emit two photons from the same storage emitter pair, they will come out sequentially, one after another. And we can distinguish them just by that, by looking at the time transient of the photons. And we can see both have the same frequency. If we do the Fourier transform of this signal, we're just going to get this peak. But we can also emit two photons simultaneously, meaning that if you just look at the time transient of the signal, it wouldn't look like two excitations. But if you do the Fourier transform, you can actually see that you have two different frequencies, one standing for each of the storage emitter pairs. So finally, what's the protocol we use to generate the 2D cluster state then? Well, it's essentially putting all these building blocks together. It's not really that complicated. So we can start by generating this vertical entangling bond, generating a Bell state between the two storage emitter pairs. Between the two storage qubits. And then we can do CNOT gates with the emitters and let the emitters decay into the waveguide, meaning that we now have this 4-photon state with these 3 entanglement bonds, which stand for the 3 2-qubit gates we have run so far. We can now run another vertical entangling gate to generate this sort of this square, which is going to be like the basic unit of our 2D cluster state. And we can now just repeat this process again and again, more CNOT gates, more CZ gates vertically to create more and more bonds in your lattice. And finally, you can run a final vertical entangling gate and a swap gate to leave this chip back in the ground state and emit all your excitations as photons traveling through your waveguide. So we can use the previous method that I've mentioned for the reconstruction of the states for the tomography, and we can infer the state that they're at, and we can see some results. So for the basic unit, for the 2x2 4-photon cluster state, we have a fidelity of 86%, and we can see here how the ideal target density matrix of the state compares to the real one. And we can see that although there is some noise, there is a very clear structure of essentially positive and negative signs, which encode this entanglement structure of the state. And it is quite well respected in this 4-photon state. And we can scale up. So we can now do a 2x3 state involving 6 photons in total, which we have measured to have a fidelity of up to 78%. We can again see the ideal and the experimental data here, and we can see that this entanglement structure is preserved. And we can actually go all the way up to, in theory, as many photons as we want. In practice, we are limited by coherence times. And for example, do a much bigger state with, for example, 18 photons here, a 2x9 ladder, which in this case has a much lower fidelity. It's below 10%. Of course, because if you have many more photons, your fidelity is going to decay exponentially with the number of photons. But you can still see that in this case, okay, I was picturing the real part of the density matrix here. Sorry that I did not mention that. If you look at the face of the density matrix now, you're gonna see that still there's this structure underlying, and this phase and these positive and negative signs standing for the entanglement are still there. So if we look at the lowest energy subset of your density matrix, that is very clear. And if we look at the corners of the matrix, which are much more affected by dephasing, we can still that the result is much more noisy, but we can still see this entanglement structure here. So this is actually working. If we want finally to benchmark the quality of these larger states, because the fidelity is of course pretty bad, we can think of how to measure the long-range entanglement in these states. And we're going to use a metric called localizable entanglement between the first and the last photons in our ladder, no matter how big it is. And what we're going to do is to project the remaining photons in post-processing in different bases. These projection recipes are just pure theory, and I don't need to explain them here. But essentially, they allow us to map our big state to a Bell state between the first and the last photon in the lattice. And we can then measure the quality of this Bell state by measuring, for instance, its negativity. And we can see something like this. So this plot contains a lot of information, but I just want you to look at the purple boxes here. This is the localizable entanglement between the first and the last photon of the ladder. as a function of the size of your state. So we have a 2 by 2, 2 by 4. So yeah, 2 by 1, 2 by 2, 2 by 3, 2 by 4 state. And we can see a non-zero localizable entanglement all the way up to 2 by 6 photons, meaning that we have in total 12 photons in our state, and we still can find some localizable entanglement between the first and the last one. Let me conclude. So I have shown that superconducting circuits are a reliable platform for quantum physics experiments with many applications, namely on quantum computing and error correction, and also in quantum optics and waveguide QED. And in particular, we have demonstrated an architecture to generate 2D cluster states, which is in principle scalable to not 2 by n photons, but m by n, by just adding more qubits to the sample. And which can also, by the way, be used to generate also other interesting states, which I have not mentioned here, but which also have applications in this field. Let me finish by thanking the team, which we have been working with for this, and I am very happy to answer any questions.
Thank you very much, Alonso. It has been a very interesting talk. So let's start. As you have said, let's start with the questions. If anyone has one, don't hesitate to start talking and to ask Alonso what you want.
Hello, I have a question.
Mm-hmm.
It's quite practical. It's just that I'm seeing precisely in this slide that says in preparation. What's left? Are you still? Are you still measuring things, or do you already have all the data?
What's left? Well, you can see here, for instance, that when we compare the results that we infer from direct tomography on our states to the coherence limit, to some other simulations, to the fidelity of our gates, and to some process maps that we use, we still don't have a very good matching between those. And we want to understand because why we have this sudden drop in fidelities when we go from 6 to 8 photons. So we are kind of finishing that. This is not the latest data set, actually, but yeah, we're still trying to polish the data, and yeah, essentially we're working on that.
Okay, yeah, because the whole protocol is clear that it works, right?
Yeah, I mean this project has been going on for many years already. Like it's not starting now. Yes.
Great. I'm looking forward to read it.
Thanks, Guillermo.
Any more questions?
Hi, Alonso. Can you hear me?
Yes. Yes.
I am Inigo. Congratulations for the talk. It was very clear, a very clear presentation. Also,
Thank
thanks. I have a couple of questions. If you could answer, I don't know. So you were telling us that you have some decoherence that degrades the fidelity, no?
Yes.
Could you comment a bit more what is the nature of this decoherence? So does it have to do with the photons traveling in the waveguide, or does it have to do with the qubits and their coupling to the environment? Or
Yes. So there are essentially two sources of decoherence in the system. One of them is the decoherence in the qubits themselves. They have reasonably good coherence times, around 20 microseconds, I would say. But essentially, as these cluster states are a huge state with a lot of phase coherence and a lot of superposition everywhere, we suffer quite a lot from dephasing. That's one source of decoherence. And the other one is, as you properly said, photon loss in the waveguide. So we can estimate that this photon loss is not very big, to be fair. We have measured, we have run some independent calibrations of the power of these emitted fields with, let me show this. by measuring a Mallow triplet and photon blockade in the system. And comparing that to the power of a single Fock state, we have more or less found that we do not have so much loss, but that's still present in the system, and that also acts like a T1 decoherence in your states.
Okay, thanks. Also, maybe it's a bit of a weird question, but it was very nice to see the measurement of the photons. So you said that you were transforming the gigahertz, I guess gigahertz photons to megahertz or so, and then you were showing some pictures of the quadratures of the measurement in time of quadratures, right?
Yes.
So
let me go back to that. Yeah.
I wanted to ask you what are the so I understand the envelope, right? This is a bit of I'm a theorist, so can understand a bit the shape of the envelope, but the faster oscillations, to which frequencies do they correspond? Do you know?
Okay. So first of all, if you look at these photons, you can see that there's this envelope, there is a very fast carrier frequency, and there is some beating also.
Exactly. Yeah.
The beating, we are not entirely certain where it comes from. It may have to do, for example, from the fact that we have some contributions of different frequencies, which are essentially the opposite sign of the frequencies that we generate. That may have to do with time delays in the acquisition devices, tiny time delays in the acquisition devices, causing you to see some sort of very slight squeezing of your phase space in one direction. And that's one thing. But the carrier frequency itself is the carrier frequency that comes originally from the frequency of the qubit. So if we have a qubit at 5 gigahertz and we emit then a photon at 5 gigahertz and we downconvert with this heterodyne detection scheme using an LO, which is, for example, 250 megahertz apart from this carrier frequency, the final frequency of the signal we're going to measure is going to be indeed 250 megahertz. So this frequency here you see is the tuning between your photons and the local oscillator in the heterodyne scheme.
Okay. And does it make sense to ask to how many photons does a single photon translate after this amplification you?
Oh, right. Okay. So we amplify these photons with a TUPA, with a traveling wave parametric amplifier. It's a Josephson amplifier, which uses a nonlinear waveguide and a pump signal and so on. And at the output of it, we already have a signal which is not a single photon anymore, but like much larger. And it's actually already projected onto a coherent state. So the projection of the photonic state happens in the amplifier. And after that, this projection is so you can think of this phase space distribution of this histogram. You can think of this histogram as a coherent superposition of many coherent states in many different directions. And when you project your photons in your amplifier, you're essentially projecting your state onto one coherent state in some of these directions. So what you measure at the end in your digitizer, when you acquire the signal here, is already a signal of a coherent state.
Okay. Yes. Thanks. Thanks a lot for the answers.
You're welcome.
Okay, thank you, Inigo. More questions?
I'd like to ask another one, if I can.
Yes, of course.
If you go to the last slide with the circuit, the final circuit with the
yes,
the real circuit.
You mean this circuit, or
that one? This one.
Okay. Yes.
The one. So basically, you have these two qubits with different frequencies, and then they go to the same line, multiplexed, because there is enough bandwidth, I guess, no?
Yes.
So the bandwidth is much bigger than the line width of the packets. And if you were to scale this, would you add more qubits and emit all of them to the same line, or would you add more lines?
Well, that's a design choice to be made. But if you want to benefit from this multiplexing, because I mean, ideally, you don't want to have, I don't know, if you think about the future and about somehow magically transducing this to an optical fiber and sending it through some cables through 3,000 kilometers, you don't want to have one optical fiber per qubit. You want to have all of it multiplexed on the same line as if possible. So in principle, one would probably prefer to multiplex this communication or this emission of the photons. One key thing to notice about this scheme is that we have a T-junction here, and effectively we can use this scheme only because the path from this T-junction to each of the qubits is much shorter than the wavelength of the photons we emit. If we were to put more qubits and we have to make paths to all the qubits, then we're going to have reflection effects in these along these paths when we emit the photons, and this is going to cause destructive interference or consequently a much lower emission rate. Your photons will become much longer because the effective coupling to the waveguide due to these reflections is smaller.
Okay, yeah, interesting. No, I was asking because I did some studies of how many photons could you fit in this.
I saw your paper. Yes.
And yeah, no, I wanted to know just if in this particular design it was a constraint, or you could in principle.
Not really, not so
more.
far. So the waveguide is not really terminated at the other end. It doesn't have a capacitor on the other end, so it's the bandwidth of the waveguide is pretty big, I would say. Possibly one of the main constraints could eventually, if you wanted to scale this up, be the bandwidth of the tuba, of the amplification, because this amplifier has a certain gain for a bandwidth of, I don't know, some gigahertz. So if you want your photons to be as fast as possible, they're going to be broader, and then you eventually might end up suffering from something like this.
Yeah, okay, very interesting. Thank you very much.
Thank you.
Thank you, Guillermo. More questions? If not, I have a. I was just, maybe it's a silly question, but I was curious about why it is convenient to have 2 qubits, to use 2 qubits for preparing the photon state instead of preparing it directly in the emitter qubit.
Because the emitter qubit, you cannot really operate coherently. The lifetime of this emitter qubit is nanoseconds because it's very strongly coupled to something going out of your chip.
Okay.
So you cannot really do single qubit gates coherently here. You cannot also do 2 qubit gates like a CZ gate, which I mentioned before, between 2 emitter qubits because just their lifetime is too short. They decay and you want them to decay fast. So it's two different things. You want some part of your sample to be coherently operatable and some part of your sample to be very strongly coupled to the environment, and that's in a huge conflict with each other.
Okay. And okay, thank you very much. Thank you. And just a quick one, just more related with the experimental setup. I was curious about. I think, for example, here or also in the 27, in the slide 27 that I saw. Why in the experimental setup of this superconducting circuits there is use a square lattice to have the qubit also. I mean,
There is no reason for that.
I guess there is. It's just a choice, or
it's a matter of okay. I mean, you need some order in your samples because you need to fit many things, and you need to be able to think in some rational way on how to distribute all these components in a device. But it's not necessary. Like for example, IBM uses these heavy hex devices in which they want to run error correction codes on devices with a connectivity of a hexagon, and then their connectivity is a hexagon then. Or for instance, there are other people working on big devices for other experiments, which, for example, skew these couplers and make like some sort of trapezoids out of them, and so on. So it's not really necessary, but it's probably convenient if you want to. I mean, also, the more ordered that this is, the more clear it is when you look at it. And it may also be an interesting feature to try and aim for.
Great. Thank you very much, Alonso. I don't know if anyone has some last questions. And if not, we'll leave Alonso rest. He has answered a lot of questions. I know. Okay, let's wait one moment if someone has more questions. Okay. So I think this is it. Thank you very much, Alonso. It was an
Thank you.
absolute
Actually,
pleasure to have you here.
yeah,
And
it's been a pleasure. Thank you very much, Jesus.
And then I think we can have this finished. So we will stop the recording and the Zoom. Thank you very much for coming. We talk now in preview. Thank you, Alonso.
Bye, everyone.
Thank you very much.
Bye.
Thank you very
Bye.
much.
Bye, thank you.
Thank you. Bye.